Imagine you only speak English and you try saying hello to a friend who only speaks Japanese. They hear gibberish. The problem isn't that your friend lacks intelligence. It is simply a language mismatch. You need a translator. Now, map that exact scenario to programming. You are the programmer and the computer is your friend. You sit down and type a standard command, like printf hello. The computer looks at that text and sees nonsense. It exclusively understands native binary code, strings of ones and zeros like 10110100. The result is the exact same communication failure. Writing code means you aren't talking directly to a machine. You are writing in a human-friendly format, which means you have to solve a core translation problem before the computer can execute a single action. To see why a computer is restricted to binary, look at what it actually is. The CPU is built from microscopic electronic circuits, operating strictly on two physical states, electrical current on or off. They map perfectly to digits 1 and 0. When you write human logic commands, words like if, while, or for, there is no physical equivalent for them on the hardware. You cannot feed an if statement into raw gold pins. The laws of hardware physics are fixed. Since the processor cannot learn our language, our software has to adapt and speak binary. This diagram illustrates the foundational architecture of compiler design. We use a software factory called a translator. Its entire job is to bridge the gap between human logic and hardware constraints. On the left, the source program is the input language written in C, C++, or Java. On the right, the factory produces the target program, the exact machine code the hardware wants. Let's test this. If you write A equals B plus C, who understands that directly, the CPU or the compiler? It's the compiler. The code routes entirely to the translator, bypassing the CPU. No modern code ever reaches the processor without passing through this translator factory first. In the first generation of computing, programmers wrote pure binary manually. It was brutally inefficient, pushing human concentration to its absolute limits. To solve this, second-generation languages introduced assembly. Programmers wrote simple text commands like MOV or ADD, and a very early translator, called an assembler, converted them into binary. By the third and fourth generations, we developed high-level languages like C++ and Python. These read almost like plain English. But to process this advanced syntax, we had to build much more complex translators, known as compilers and interpreters. As programming languages became significantly easier for humans to write, the underlying translator software had to become drastically more complex to handle the conversion. The 5-stage pipeline. A human writes high-level language. That feeds into a translator, outputting machine language for the CPU. As computing's central mechanism, we will soon break open this translator box, exploring the lexical analyzers, structural trees, and state machines, making this conversion possible. Compiler design is simply the deep dive study of how this singular, crucial bridge is built.